Hey all, today we'll be doing the Princeton University Science Olympiad exam for astronomy in the 2026. This is the first question in the free response section for mathematics, and let's get into it. So we're presented a system with a pulsar and another compact object, and that's shown in figure 1, the radial velocity curve, and then we'll talk about this a little bit later. But so first off, the question, the later parts, just to keep things simple for the solution, on the later parts, we assume that m1 equals m2. So you're assuming that these two objects, they're basically both pulsars. They have the same mass. And one thing to observe is that from this curve, we're observing a perfect sinusoid. So since it's a perfect sinusoid, we expect that the eccentricity is 0. And so for zero eccentric systems, the best way you can draw this image, which is the correct image, is that you have a circular orbit, right? And you have both pulsars on this circular orbit, m1 equals m2, and they're orbiting about a common center of mass right here. So that's the image we're dealing with, and the first question asks us that basically we can't use Doppler shifting of absorption lines to get the radial velocity. So how do we get the radial velocity? And the way you go about doing that is kind of a cool principle, is that for any wave phenomenon, the observed frequency is modulated by this equation here. This is in like the low velocity case, non-relativistic. And so like this is just Doppler shifting for waves, I guess, wave fronts, wave crests. And what happens here is that with their velocity convention, so that as the pulsar is getting closer to us, the velocity is going to be negative. So you're going to have F emitted. This will be basically 1 plus v over c, where this is like the magnitude of the velocity, F observed. So then this will be positive, and as the pulsar is getting closer towards us, your frequency will be greater. Same thing on the other way, where when the pulsar is moving away from us, we're going to have 1 minus v over c equals F emitted and F observed. So this will be lesser or smaller. So basic idea is that as the pulsar is moving towards us, we're going to observe greater frequency of the pulsar timing, like the pulsar signals. And as it's moving away from us, we're going to see a lesser frequency of the pulsars. And from that, we can infer what the velocity is of the system. So that's how you get graphs like this. So you can kind of just write quickly, I guess, like infer velocity from changes in pulsar timing, pulsar frequency. From changes in pulsar frequency. Pulsar frequency. So that's the first step for this question. So that's 2 points there. Now from the radial velocity curve, can we deduce eccentricity of the orbit? We mentioned this earlier, but eccentricity is 0 here. And that is from the sinusoidal nature of this curve. That's like the geometric consistent image there. Okay, so I guess a big point is that the amplitudes are symmetric. So then the next part is it says compute the pulsar's orbital semi-major axis in astronomical units. So what you're going to do here is the convenient part is that this is a circular orbit. And so for circular orbits, anytime you have a circular orbit, you're going to have the principle that the velocity is going to be equal to the circumference of the orbit divided by t, right? And so this semi-major axis in the circular case is just like the radius of the circular orbit. So then r is equal to vt divided by 2 pi. And then reading off the graph, we can state, what can we state here? We have that the velocity is 300 kilometers a second. And it seems like the period here, if I'm not mistaken, it looks to be around 3.5 hours, if I'm not mistaken. So then 200 kilometers a second times 3.5 hours divided by 2 pi. You can do the dimensional analysis here. You know that there are 3,600 seconds in an hour. When you do that, you're going to get that this is 6 times 10 to the 5th kilometers, which is equal to 0.004 AU. So that is the orbital semi-major axis of the pulsar. Okay, the pulsar arrival times also vary sinusoidally, as shown in Figure 1b. And this is due to the fact that the pulsar's distance to Earth changes through its orbit. Compute the semi-major axis using this data. So this is actually really cool. It has to do with like a geometric delay. So if you have our system here, and let's say Earth is here, right? And then we're going to have the pulsar should be on opposite sides for this image. So what you're going to have here is that, can I move this image? You like have some expectation of when the pulse should be arriving. And what essentially happens here is that compared to, say, perhaps this point, your pulse takes additional time to travel to Earth. So compared to, like, let's say this is the average right here, when the pulsar is on this side, the light is gonna have to travel an extra this distance. And this extra distance is 2 times the radius, right? So what you're gonna want is 2 times the radius, and you know that distance is equal to velocity times time. So for light, this is always gonna be the speed of light, 10 to the 5th kilometers a second, speed of light. And the time, it says here that your timing delay is a total of, compared to the baseline, it's 2 seconds. And it's a 4-second difference from when the pulsar is here. So here we're gonna put in 4 seconds. No, 4 seconds, right? Let's see. It's gonna take, let's see, yeah, this should be right, because that's the time it takes to travel this distance. Yep, okay. So then doing this math, you should get that the distance is also 6 times 10 to the 5th kilometers. I guess it's not too bad to get, because then, I mean, it's kind of obvious. 4 seconds here, you divide by 2, and then you get the same 6 times 10 to the 5th above. Okay, so same 6 times 10 to the 5th kilometers, which is equal to your 0.4 AU. So these two cases are consistent with each other. So that's good. Okay, and that's just off the geometric delays, where when the pulsar is here, its light is going to take a little bit longer to reach Earth, and the light is going to have to travel this much distance, and this much more distance compared to its standard pulsation arrival time. Okay, so the next question is that suppose both objects in the binary have the same mass, compute the mass of the pulsar. Okay, so this is Kepler's third law, and we have that t squared is equal to a cubed over m total. So we definitely know the semi-major axis, good, and we also have the period, I believe, so we just can get m total. So then m tot equal to, what is this, 0.04 AU? 04 AU. AU. We're going to cube it, and we're going to divide by t squared, where t is still your 3.5 hours from earlier. 3.5 hours. And you want to convert this to years. So quick fun fact is that there are 3.154 times 10 to the 7th seconds a year. Pretty sure that's right. Something close to that, like 3.1 seconds in a year. And so you can convert this to 3,600 seconds an hour, and then do 3.154 times 10 to the 7th seconds a year. Because when you're doing this form of Kepler's third law, you're going to want everything in terms of AU and Earth years. And if you do that, you'll get your units in terms of solar masses. So then doing this, you should find that the total mass, let's see. Oh, also, you want to make sure that the semi-major axis you use for Kepler's third law, you need to use the total semi-major axis. That's one thing I forgot to correct. So instead of 0.04 AU, it's actually going to be 0.08 AU. And we can draw the total image a bit later. But this is the total semi-major axis here. And when you do this calculation, you're going to find that m tot is equal to 3.2 solar masses. So the mass of an individual pulsar is about 1.6 solar masses. So m1 equals 1.6 solar masses right here. I can draw the picture for this in a later step because we'll need it in a few seconds. Okay, so that's this part of the problem solved. Now let's move on. So this is a long thing you can read, you can pause it, but the basic goal is that we want to calculate. We just want to calculate the gravitational waves that are emitted when the system has a separation of 0.01 AU. So this is kind of just plugging in the formula. Nothing too much to do here. 10 to the negative 11. If we have to throw in the units, it looks like this. Meters squared, kilograms squared, times 3.0 times 10 to the 5th. Let's make it 10 to the 8th to be consistent. Okay, so I'm just plugging the formula right now, by the way. So mu, we can calculate as m1 times m2 divided by m1 plus m2. So then mu is equal to 3 over 2 times 3 over 2 divided by 3 over 2 plus 3 over 2. So this is equal to 9 over 4 divided by 6 over 2. What we're going to do is we're going to take the reciprocal, and we get this is 3 over 4. So then 3 over 4 to the second power, multiply by 0.01 AU times 1.5 times 10 to the 11th meters per AU. We're going to take that number to the fourth power, and then all we need to get is the pulsation frequency. So W to the fourth here. Now to get W, for this step, you're going to get W from the pulsar. Let's see, is this the same problem as before? Yeah, so to get W, you can just say that W equal to 2 pi over T, where, I mean, this is just your frequency of the system. And from earlier, we know this is 3.5 hours, right? Which is a little bit different because I guess the mass changed a little bit, but that's okay. Same thing with the semi-major axis. That's okay. Okay, so let's see. Okay, so using this result, we're going to find that putting in the angular frequency, this is 3.5 hours times 3,600 seconds an hour. Raise it to the 6th power. Your result is that LGW is going to be equal to 4.7 times 10 to the 24 watts, which is about equal to 0.12 solar luminosities. So that's kind of cool. It has like 1% of the solar luminosity emitted in gravitational waves at this separation axis and orbital speed. Okay, so next question here is that we're almost done, only 2 more parts. So first part is the orbit will decay due to the emission of G waves. Neutron stars are about 20 kilometers inside, so the merger point is when the orbital separation is about 20 kilometers. Okay, so it wants us to compute the relative orbital velocity of the binary with this formula, where m is the total mass. So this is a relative system, which is kind of cool. So what you do here is that this is m1, you can say this is v1, and this is v2, right? And this is the barycenter here. So what happens is that the relative orbital velocity is going to be v is equal to v1 minus v2, I believe, is going to be defined as v1 minus v2, which is going to look something like this. This is our v1 velocity. This is for the center of mass system, right? So for the center of mass system, what you have is you have vrel equals v1 minus v2. v2, you're going to take this vector, flip it the other way, and this is your v2 now here. So your total v relative, or v total, vrel looks like this. And it's basically saying that the problem can be the equivalent system of twice the total mass of the individual masses is what the problem reduces down to, which is kind of the similar reason why for the semi-major axis earlier, we had to use a1 plus a2 cubed over m total. So this is your velocity here. And so what you're going to have is to compute the v, going to be, 6.67 times 10 to the negative 11 newtons, meters, kilograms squared, times your total mass, which in this case is still 3.2. 3.2, or no, this is going to be 3.0 times solar masses times 2 times 10 to the 30th kilograms per solar mass, and then divided by your 20 kilometers. So this is going to be the total velocity, and if you plug this in, you'll get that v is equal to 1.4 times 10 to the 8th meters a second, which means that the velocity of an individual pulsar here is going to be like 7 times 10 to the 7th meters a second. Wait, did I do that right? 0.7 times 10 to the 8th meters a second. Sorry, y'all. Okay, and this is pretty close to the speed of light, because speed of light is 3.0 times 10 to the 8th meters a second. So we are moving at about 0.2 times the speed of light, so pretty fast to it, but that's okay. Okay, so last part of the problem asks us how luminous will the system be in gravitational waves at merger, and to answer in terms of solar luminosities. So we're going to apply the same formula from before, which was right here, namely that it is LGW equals 32. Actually, I can just copy this formula from before and then change a few numbers, so that'll be nice. So we're going to write this formula down here. And what do we need to modify here? So this is all fine. This mu formula should be the same. That doesn't change, same mass. Your orbital axis is going to change. Now this is going to be 20 kilometers. So 20 times 1,000 here. And then your period evidently changes. So here we're using the notion that W equals V over R. So we still have our this will be the relative velocity, right? Yeah, it should be 1.4 times 10 to the 8th meters a second divided by 20 kilometers. I guess just be 20,000 meters. This is going to give you angular velocity of, I don't have it written down, that's okay. So you're going to plug that into this part right here for the new angular frequency. Should be a lot faster though. So put that in here and then raise it to the 6th power, and you'll get your gravitational wave luminosity. And this here is going to be L merge is equal to 2 times 10 to the 22th solar luminosity. So it's highly efficient. And in watts, that's going to be 7 times 10 to the 46th watts. So very, very luminous in gravitational waves at the point of merger. I guess one thing is you can do this calculation right here, since this is 1.4 times 10 to the 8th times 2 times 10 to the 4th. So then you're going to get like 0.7 times 10 to the 3rd for your frequency. So yeah. Oh wait, this should also be replaced for your general frequency here. This will replace that entire frequency right here. Okay, y'all. So that is this problem. If you have any questions, feel free to drop it in the comments below. But good luck with studying. So yeah, take care.